Hello everyone, my name is Omkar Upadhyay and I am presenting my project Krishi Mitra. This is a multi-agent agricultural intelligence system designed to process complex multi-domain farming queries using an supervisor worker framework. The problem I set out to solve sits at the intersection of agriculture and AI architecture. Farmers deals with complex workflows like share cropping disputes, precise NPK fertilizer maths, and live seed subsidies. Currently, they are forced to navigate fragmented, rigid, and static government web portals. You might ask, why not use ChatGPT? Because generic large language models suffer from two fatal flaws in this domain. First, they hallucinate the localized data. Second, they crash when given multi-step tasks with missing parameters. The project objective is to build a supervised framework, a supervisor, and a 10 specialized worker agents powered by dynamic retrieval. This is my system architecture with one supervisor and 10 workers having different specialized tools. When a user asks query, supervisor agent look at the user's message and decide who acts next. To build this, I used LangGraph for state orchestration and the Gore KPI running the GPT OSS 120B model for reasoning. Because agriculture requires real-time accuracy, I bypassed a static way. Instead, the agents are equipped with dynamic web search pipelines like Tavli and DuckDuckGo to retrieve the live market or weather data directly from the internet. To break the infinite loop or multiple hop, I used safeguard in the supervisor node. First, it checks the last sender in the state. If it's a worker, the system forced to finish. We will see this during the code demonstration. We will see the tracing data in Langsmith during demonstration as well. Now let's start our code demonstration part. Now let's start with the state. Everything begins here with the Krishi Mitra state. In LangGraph, the state is shared memory passed between agents. Notice that I am using add message reducer. This is crucial. It appends new messages to the dialog rather than overwriting them. I also explicitly track next for routing and sender so that the system always knows which specific agent just executed an action. Now look at the graph.py. I have 10 domain-specific workers. Instead of writing 10 separate functions, I engineered this make worker node function. Notice this string grok safeguard. This is critical architecture design because earlier whenever I pass edge cases, such as missing parameters in the queries, either my system trapped in infinite loop or it takes multiple hops, which is undesirable. I applied a strict instruction to every single worker telling them if you lack a required parameter, do not guess. Use the ask user for missing data tool. By injecting this into the system prompt of every agent, I prevented the LLM from hallucinating variables like district name or crop types. The supervisor node. This is the brain of the supervisor and worker topology. The supervisor, its only job is to look at the user's message and decide who acts next. Notice this class route using Pydantic by forcing the LLM into JSON mode and strictly validating the output against this Pydantic schema. I completely eliminated a common LangChain error, which the model outputs invalid tool calling formatting and crashes the API. Here is the most important safeguard in the entire system. In early testing, agent would answer a question and send it back to the user, and the supervisor would mistakenly send it right back to the agent, creating an infinite expensive API loop. To solve this, I built a programmatic short circuit. The code checks last sender If the last message came from a worker like Umi or Mosam, the Python code intercepts it and forces a finish state. This instantly halts the graph, returning the final answer to the user and prevents the cyclic hallucinations. Finally, we compile the graph where every worker has a directed edge back to the supervisor, and the supervisor uses conditional edges to route to the workers. This creates a highly scalable, fault-tolerant state machine. Let's see this architecture in action. I will type find cold storage for Makhana in Dharwanda. The supervisor processes this, bypass the other 9 nodes, and route exactly to the supply chain worker. This worker uses its search tool and returns the live data. Here you can see the execution traces. Now I will trigger the safeguard we just looked at in the code. I will just type one. Notice what happens. The system does not crash. The Mosam agent realizes its missing location, triggers the asks user for missing data tool, and loop breaker halts the graph to ask me which district. The state machine is perfectly stable. Now let's connect to the repository. This is my system architecture. Now let's see this. Here you can see latency, tokens, metadata, threads. Now see why this error happened. We can observe everything here. You see alarm counts, alarm latency, output tokens, blood trace. See how agents to wrap up. Building Krishi Mitra taught me that a multi-agent system fails without strict data governance. You can't trust an LLM to manage its own state transition natively. However, there are limitations. Maintaining conversation history across 11 total nodes, causing high token consumption, and the system speed is ultimately bottlenecked by the rate limit of external APIs. For future scope, the next step is integrating interface like speech to text to bypass the literacy barrier for farmers and adding computer vision nodes for crop disease diagnostics. Thank you. For more details, please check my Medium article given in the description. Thank you, Ansari.